If you stop absolutely anyone on the street, from a grade school student to like a retired engineer,
Yeah.
and you ask them for the one unbreakable rule of gravity, they're all going to give you the exact same answer.
Gravity attracts.
Exactly. Gravity tracks. It pulls. It is the invisible cosmic glue that keeps our feet planted on the sidewalk. It keeps the moon tethered to the Earth, and it keeps the Earth just endlessly orbiting the sun.
Right. It's the fundamental baseline of our physical intuition.
Yeah. I mean, from the moment Isaac Newton supposedly watched that apple fall in his orchard, all the way to Einstein mapping the four-dimensional curvature of space-time.
Yeah.
The observable truth of our universe has always been that mass pulls other mass toward it.
Yeah, in general relativity, mass bends space-time to create a well, and things naturally fall into that well. Gravity strictly, exclusively attracts.
Right. But here's where it gets really interesting. Because a brand new theoretical proposal sitting right here on the table in front of us mathematically predicts that if we carefully set up an exquisitely specific quantum environment, a group of probe particles could receive an average gravitational kick entirely in the opposite direction.
A kick away from a nearby source mass.
Yes.
A kick away.
It sounds like a complete violation of every physics textbook ever printed.
Oh, absolutely.
When you first encounter a headline suggesting that gravity could push instead of pull, your mind immediately jumps to science fiction. You picture warp drives or levitation technology.
Hoverboards.
Right, hoverboards, or some undiscovered exotic matter with negative mass. But what's fascinating here is that this specific proposal does not require modifying Einstein's general relativity at all.
Okay, wait, really?
Truly. And it absolutely does not require inventing a new, exotic fifth force of nature. It relies entirely on the established, heavily tested mathematics of standard quantum mechanics intersecting with gravity. Okay, I want to stop right there and put up a massive flashing warning sign for everyone listening, just so we don't accidentally start like a runaway internet rumor.
Good idea.
This is not a new anti-gravity force. This is not ordinary gravitational repulsion. You cannot use this to build a levitating car, and it definitely won't help you launch a rocket into orbit for free.
Unfortunately not.
What the researchers in these source papers are actually proposing is a highly conditional quantum interference effect. It requires taking a microscopic source mass, placing it into a spatial superposition, allowing both of those branches of reality to gravitationally attract a probe, and then performing a very specific mathematical filtering process.
It's essentially the ultimate quantum magic trick.
It really is. And dissecting exactly how this trick works is the subject of this Science Candy episode for Claire and our show titled The Experiment That Could Make Gravity Push Back.
And the mission for you, listening to this today, is to look past the illusion of that magic trick. We need to understand the profound underlying mechanics of what is actually happening to the joint quantum state of these particles.
Because we have to figure out how two attractive forces can mathematically, interfere to create the illusion of a push.
Exactly. And this raises an important question. From the perspective of an experimentalist, why would pulling this off in a noisy laboratory rank among the greatest and most punishing experimental feats in the history of physics?
Okay, let's unpack this from the ground up. Because to understand how a pull can ever be mathematically transformed into a push, we first have to understand the microscopic architecture, where these bizarre quantum rules take over.
We need to look at the Mach-Zehnder interferometer.
Right. And usually when you hear about interferometers, we're talking about light. You fire a single photon at a half-silvered mirror. The photon's wave function splits, so it travels down two separate physical paths at the same time.
Path A and Path B.
Yeah. Then it bounces off some mirrors and recombines in a second mirror. And depending on the length of those paths, the light waves either add together or cancel each other out.
Sure.
But here, the source traveling through the interferometer isn't light.
No, it's a massive object. Specifically, the proposal suggests using a nanodiamond.
A microscopic diamond. So what does this all mean? Like, why a diamond?
Well, it's crucial to understand why they specifically want a nanodiamond rather than, say, just any microscopic speck of dust. A nanodiamond is a tiny crystal lattice of carbon atoms, but the researchers want a diamond that has a very specific manufactured flaw inside of it.
Okay, a flaw?
Yeah, it's called a nitrogen vacancy center, or an NV center. This happens when a single nitrogen atom replaces a carbon atom in the lattice, and the space right next to it is left completely empty.
Huh.
This defect acts almost like an artificial atom trapped inside the diamond, and it has a property called quantum spin, which, importantly, responds strongly to magnetic fields.
Right. The spin is like the handle we use to grab the diamond. By hitting this NV center with a precisely tuned pulse of microwaves, physicists can put the spin of this defect into a superposition of being both spin up and spin down at the exact same time.
Exactly. And then they apply an intense, highly localized magnetic field gradient.
Okay, and because of, it's the Stern-Gerlach effect.
That's right. Because of the Stern-Gerlach effect, the magnetic field physically pushes the spin-up version of the diamond slightly to the left into path A and pushes the spin-down version slightly to the right into path B.
And just like that, the entire macroscopic diamond crystal is now hovering in a spatial superposition. I mean, think about it. It's physically located in path A and physically located in path B simultaneously.
It hasn't split in half. The entire mass is occupying two distinct coordinates in space.
Which is just wild to try and wrap your head around.
It is, and this is the precise moment where the gravitational interaction begins. We introduce a second object, which we'll call the probe particle. We place it nearby, completely outside of the interferometer.
Okay, so the diamond is inside the machine in two places at once, and the probe is just sitting outside.
Right. The proposal suggests using a cloud of atoms trapped in a highly localized standard quantum state for this probe. Now, if gravity itself is fundamentally a quantum phenomenon, the gravitational field generated by the source mass must also enter a superposition.
Because a classical field can't do that.
Exactly. A classical field cannot couple to a quantum superposition without collapsing it. Therefore, the probe particle does not feel a single, smeared-out, average gravitational pull. It's simultaneously subjected to the distinct attraction from the diamond in path A and the distinct attraction from the diamond in path B.
But, and here's where we hit the conceptual wall, both of those pulls are strictly 100% attractive.
They are.
Like, let's really hammer this home. If we isolate the math for just one branch, if the diamond is sitting in path A, its mass bends the local spacetime, and the probe receives a positive momentum kick. The researchers call it delta A, right?
Yes.
And that literally pulls the probe directly toward path A.
Right.
And if we look at the other branch, if the source is in path B, the probe receives a different positive momentum kick, delta B, pulling it directly toward path B.
Because the paths are at slightly different distances from the probe, the magnitude of the force is slightly different in each branch.
Right, but there is absolutely no negative force here. Both branches are unequivocally pulling the probe towards the source mass.
Which forces us to look at what is actually happening to the joint quantum state of the two particles during this interaction. Because the probe's momentum changes conditionally, meaning its exact shift depends entirely on exactly where the source mass is located, the two particles become quantum mechanically entangled.
They become linked.
Inextricably linked. The gravitational force acting on the probe has become mathematically dependent on what we call the source position operator.
Okay, wait, before we breeze past that, let's translate operator for a moment. In quantum mechanics, an operator isn't a physical thing you can hold, right?
Right, no.
It's essentially a mathematical instruction. It's an instruction that you apply to a wave function to extract a specific observable property, like momentum or position.
That is a perfect way to describe it. In classical physics, a particle just has a position. It's sitting at coordinates x, y, and z. But in quantum mechanics, a particle has a wave function representing a cloud of probabilities.
So to find out where it is.
You apply the position operator, which essentially asks the wave function, where are you? And because the gravitational force in this setup now depends on this position operator of the source, the evolution of the probe's wave function is intimately tied to the superposition of the nanodiamond.
We're no longer dealing with a diamond in a separate probe.
No, we are dealing with a single, entangled, bipartite quantum state. And that entanglement is mediated entirely by gravity.
Okay, so here's where my brain starts to twist into a knot. And I suspect you listening are hitting the exact same logical wall. If the probe is entangled, and both of these branches, path A and path B, are independently transferring positive attractive momentum to the probe, pulling it closer, how do we possibly arrive at a final state where the probe is moving away?
It seems contradictory.
It does. You cannot add two positive numbers together and get a negative number. If I push a shopping cart forward with my left hand and push it slightly harder forward with my right hand, there is no physical universe where that cart rolls backward toward me.
If we were operating in the realm of classical physics, your logic would be absolutely flawless. A classical mixture of two attractive trajectories will always, without exception, yield an attractive trajectory.
The shopping cart only goes forward.
Exactly. But what's fascinating here is that we are not adding physical forces or classical trajectories. We are manipulating quantum wave functions. The secret lies in a process called destructive interference, combined with an active filtering mechanism known as post-selection.
Post-selection. Okay, let's unpack this, because this is the absolute secret sauce of this entire proposal. It's the key to the whole illusion. Post-selection is, at its core, a ruthless filtering process, isn't it?
It absolutely is.
So in the experiment, we let the nanodiamond travel through the two paths. It interacts gravitationally with the probe for half a second, and then the two paths recombine at the exit. The magnetic fields merge the two spatial locations back into one.
Right, they bring the superposition back together.
But here is the trick. We do not look at all the experimental runs. We place quantum detectors at the exits of the interferometer, and we intentionally throw away the vast majority of our data.
We explicitly choose to only keep the data from the runs where the nanodiamond exits in a very specific rare state.
Which is the dark port.
Yes. In classical optics, when you recombine light, the beams can interfere constructively, so a bright beam comes out one port, or destructively, so no light comes out the other port, the dark port.
And mathematically, for our diamond, this is called an antisymmetric state, right?
Exactly. We are predetermining a highly specific, highly unlikely outcome for the source mass, and we are choosing to look only at the extremely filtered subset of reality where that outcome occurs. If the nanodiamond exits in the normal symmetric state, the bright port, we literally delete that data.
We just ignore whatever happened to the probe particle during that run.
We toss it out.
It's like running a rigged casino. You roll the dice 1,000 times, but you only record the results on the clipboard when the dice happen to land on double sixes. But how does this filtering actually create the push?
This is where we have to talk about the wave functions themselves. Because particles weren't just points, they are described by these probability distributions that have positive and negative phases. They act like ripples on the surface of a pond.
And this is where the classical shopping cart analogy breaks down.
Completely. In classical physics, probabilities are just a measure of our ignorance. A coin is either heads or tails. We just don't know which until we look. But quantum wave functions contain phase, meaning they have peaks and troughs.
Right.
When we mandate that post-selection, when we demand that the nanodiamond exits in that rare antisymmetric state, the underlying mathematics of the universe dictates that the wave function of the probe particle associated with path A must be subtracted from the wave function of the probe particle associated with path B.
Subtract. Okay, here's where it gets really interesting. Let's visualize this subtraction, because this is the magical moment. Imagine the probe particle's momentum is a standard classical bell curve on a graph.
Okay, picture the graph.
The peak of the bell curve is right at zero. That is its initial state before gravity ever enters the picture. It's sitting perfectly still. Now we introduce the superposition. The gravitational pull from the diamond in path B pulls the probe slightly, shifting that entire bell curve a tiny bit to the right toward positive attractive momentum.
Right, a slight shift toward the source.
Now look at path A. Path A is physically closer to the probe, so gravity is stronger. The pull from path A shifts its version of the bell curve even further to the right. Both curves have moved into positive territory.
And if we just let the experiment run without filtering, those two positive bell curves would simply smear together into one larger positive bell curve. The probe would just move toward the diamond.
Exactly. But we aren't doing that. Because of the post-selection, because we demanded that dark port outcome, we are not adding those shifted bell curves together. The mathematics of that anti-symmetric state force us to subtract them.
We have to take the slightly shifted path B curve, and we mathematically subtract the heavily shifted path A curve from it.
So if you take a bell curve and you mathematically carve a giant chunk out of its right side, the positive momentum side, what are you left with?
You are actively wiping out the positive momentum probabilities. You're creating destructive interference on the side of the graph where the particle was being pulled the hardest.
Which is just crazy to think about.
It is. The remaining wave function, the only portion of the probability distribution that survives this bizarre quantum subtraction, is now heavily skewed to the left.
The peak of this new filtered bell curve now sets firmly in negative momentum territory.
Exactly. When we calculate the expectation value of this new, weirdly shaped distribution, we find a negative average momentum. But it is absolutely vital that you understand the nuance here.
Right, the disclaimer again.
We are not creating a new physical force that pushes the particle backward. We are actively, mathematically filtering out all the versions of the probe particle that got pulled the hardest. We are leaving behind a carefully curated, highly specific quantum ensemble that, on average, possesses negative momentum.
It looks exactly like it got pushed, but only because we hit all the ones that got pulled. It's
Precisely.
an incredible illusion. But even with this subtraction, the amount of momentum we're dealing with here is infinitesimally small. I mean, gravity is already the weakest force, and now we are talking about the difference between two microscopic gravitational pulls on a cloud of atoms.
It's an impossibly tiny signal.
So to actually measure this in a lab, the physicists rely on a mathematical trick that acts like a massive magnifying glass. It's called weak value amplification, or the AAV effect.
Named after physicists Yakir Aharonov, David Albert, and Lev Vaidman, who theorized it back in 1988.
So what does this all mean? How does this magnifying glass work?
Well, weak values are one of the most counterintuitive and heavily debated concepts in modern quantum mechanics. In a standard quantum measurement, the interaction is strong. It completely collapses the wave function. But in a weak measurement, the interaction, in this case, the gravitational pull, is so gentle that it barely disturbs the system.
It leaves the superposition intact.
Right, but it barely gives you any information. To extract anything meaningful, Aharonov, Albert, and Vaidman realized you could use post-selection to amplify the tiny signal.
Okay, let's unpack how that actually functions. It all comes down to how we choose the starting state and the ending state of our nanodiamond. In the proposal, the initial state of the source mass before the interaction, what we call the pre-selection, and the final filtered state, the post-selection, are chosen to be what physicists call nearly orthogonal.
Let's define orthogonal, because that's a term thrown around in linear algebra constantly.
Yeah, please.
In quantum geometry, two states are orthogonal if they are perfectly, completely mutually exclusive. The classic example is the spin of an electron. If an electron is perfectly spin up, it has exactly zero probability of being measured as spin down along that same axis. Those states are orthogonal. They share no overlap.
So in our setup,
If the nanodiamond enters the bright port is orthogonal to the dark port. If it is destined for one, it cannot possibly enter the other.
right. But the researchers don't want them to be perfectly orthogonal, because then the experiment would yield nothing. They make them nearly orthogonal. They are almost, but not quite, mutually exclusive. And here is where the math performs a spectacular trick.
This is the mathematical blow-up.
Yeah. When you calculate the expected momentum shift of the probe, the formula involves a fraction. And the denominator of that fraction is essentially the overlap between the pre-selected starting state and the post-selected ending state.
And if those states are nearly orthogonal, their overlap is tiny.
Exactly. Which means the denominator in your calculation becomes incredibly small. And as anyone who remembers middle school math knows, when you take a number and divide it by a tiny fraction, the resulting value blows up. It skyrockets.
This is the amplification factor. The researchers calculate that because they can tune this denominator to be so small, the effective momentum transfer to the probe can be amplified by orders of magnitude.
The negative kick it receives can be mathematically magnified to be vastly larger than the individual tiny gravitational pulls that originally acted upon it in either path.
This is why weak values are so heavily prized in a field called quantum metrology, which is the science of extreme precision measurement. This same amplification technique is currently used in optics to measure incredibly subtle effects, like the spin Hall effect of light, where a laser beam shifts by fractions of a nanometer.
Which normally you'd never see, right?
Right. That shift would normally be entirely buried in the background thermal noise of the laboratory, but weak value amplification blows it up so the detectors can actually see it.
But of course, the universe is not in the habit of giving away miracles for free. There's a brutal, unavoidable trade-off here, isn't there?
There is always a price. And here, the price of this massive amplification is paid directly in the currency of data loss. Because those two states are nearly orthogonal, because they are almost mutually exclusive, the physical chance of the nanodiamond actually exiting the interferometer in that specific dark port state is agonizingly tiny.
It's the tragedy of the denominator. For the specific parameters the researchers are proposing in these papers, they calculate an amplification factor of 100. That means the negative momentum kick is 100 times larger than the baseline gravitational pull, which sounds fantastic.
It does. But to achieve that denominator, the success probability of the post-selection drops to approximately 0.8 times 10 to the negative 3.
Let's write that number out for everyone listening. That is 0.0008.
It's devastating.
It really is. That
Right.
means for every 1,000 times you run this incredibly delicate, impossibly complex experiment, carefully floating your diamond and cooling your atoms. You get the dark quartz result you want exactly zero point 0.8 times. You're literally throwing away over 99.9% of your painstakingly gathered data.
All of that effort, all of that liquid helium cooling, all of that vacuum pumping, just to delete the results 999 times out of 1,000.
Just so you can see the amplified effect in that remaining fraction of a percent.
Which naturally forces us into one of the most fascinating philosophical debates in modern physics. When physicists stare at this math and they realize the amplification requires discarding almost the entire universe of data, a fierce argument erupts regarding physical reality itself.
Like, what are we actually doing here?
Exactly. Is this effect best understood as a literal physical gravitational repulsion? Did gravity change its nature? Is it an anomalous transfer of genuine physical momentum? Or is it strictly a statistical artifact, a mathematical ghost created by a filtered quantum ensemble where we have selectively and intentionally ignored the reality of all the particles that behaved normally?
I have to admit, when I read Lev Vaidman's arguments in the source material, I lean heavily toward the wonder of the anomalous momentum transfer.
You take it literally.
Yeah. The weak value isn't just a math trick. It is a property of the pre- and post-selected system.
Yeah.
As Vaidman argues, the weak value behaves as a genuine, robust physical property of that single specific system during the time interval between the pre-selection and the post-selection.
During that half second.
Yes, during that half second, the probe particle physically acquires this negative momentum. Its physical trajectory genuinely changes in a direction that is strictly opposite to the applied attractive force. I mean, it completely challenges our fundamental baseline intuition about how forces operate when they are submerged in a quantum regime.
And as an experimentalist who spends their life fighting statistical noise, I will vehemently maintain my skepticism.
I knew you would.
I will insist that it is a statistical ensemble trick, albeit a profoundly beautiful and useful one. Yes, the expectation value of the momentum for that specific subset is negative. The math is unassailable. But it is negative only because we artificially conditioned our final measurement on a highly improbable future event.
So you're saying we engineered the result by hiding the normal behavior?
Exactly. If we connect this to the bigger picture, think of a macroscopic classical analog. Imagine we have a machine that drops 1,000 apples from a tall building. We know gravity is pulling all of them straight down.
Right, standard gravity.
But imagine there are tiny, random gusts of wind swirling around the building. We stand at the bottom, and we notice that by some freak aerodynamic chance, a highly specific microgust of wind blew exactly one single apple slightly upward just before it hit the ground.
Okay, I see where you're going.
We then intentionally ignore the 999 apples that smashed into the dirt. We take a picture of the one apple moving up, and we publish a paper claiming we have discovered repulsive gravity.
Right. Though the obvious difference in our quantum experiment is that the wind isn't random air currents. The wind is the fundamental, mathematically rigorous wave nature of matter itself.
True. The phase subtraction is a real physical process.
But regardless of whether you interpret it as a physical push or a filtered ensemble, the utility of this effect is absolutely undeniable. It provides us with a potential, highly sensitive laboratory witness for the existence of quantum gravity.
Which brings up a massive question.
Yeah, let's unpack that, because if my brain can eventually accept that this is a brilliant filtering trick powered by wave subtraction, why couldn't standard normal classical gravity do the exact same thing? Why does seeing this specific negative shift prove that gravity itself must be fundamentally quantum?
To understand that, we have to look at how a hybrid theory, specifically a semi-classical theory of gravity, utterly fails to replicate this phenomenon.
Okay, let's dive into that. Let's explore that. Semi-classical gravity.
This is the crux of the entire paper. Right now, physics is broken into two separate rule books. We have quantum mechanics for the tiny stuff, and Einstein's general relativity for gravity and the massive stuff.
And they don't play well together.
They don't, because we don't have a unified theory of quantum gravity yet. Some physicists wonder if maybe we don't need one. Maybe gravity is just classical all the way down.
So what does semi-classical mean here?
In a semi-classical theory of gravity, matter, like our nanodiamond and our probe, is treated using the full bizarre rules of quantum mechanics. But the gravitational field itself is not quantized. It remains a classical, continuous, smooth, mean field.
It does not have wave functions, it does not have superposition, and it does not have phase.
All right.
Okay, so let's play out our experiment using the semi-classical rulebook.
Yeah.
In that model, The gravitational field is sourced by the expectation value of the mass distribution.
Which is a fancy way of saying gravity looks at the average mass.
Right, so when our nanodiamond gets hit with the microwaves and enters a spatial superposition, being in path A and path B simultaneously, the classical gravitational field does not split into a superposition.
Because a classical field cannot do that.
Exactly. Instead, it creates a single average gravitational potential. It creates a smeared out phantom gravitational pull that is centered precisely halfway between path A and path B.
And when our localized probe particle interacts with this mean field, it doesn't feel two distinct forces. It feels a single, classical, incredibly boring, attractive force, pulling it toward the center of the interferometer.
And because it feels a single average force, there's absolutely zero entanglement.
Zero.
The probe does not become entangled with the specific position of the source mass, because classical gravity cannot carry quantum information. It's like trying to send a high-definition video over a piece of string.
The classical field simply lacks the capacity to link the two wave functions.
And without that entanglement, without the probe's momentum being conditionally tied to the exact position of the diamond, post-selecting the source mass does absolutely nothing to the probe.
That is the fatal blow to the semi-classical model. You can filter the nanodiamonds at the exit all day long. You can select the dark port. You can select the bright port. You can throw away 99.9% of your data.
Doesn't matter.
No, because they were never entangled, the probe's wave function will just sit there, completely unaffected by your filtering, having experienced standard positive attraction toward the center. Therefore, classical mechanics, classical phase space distributions, and what physicists call classical Liouville dynamics cannot possibly generate this negative, repulsive shift.
Wait, let's define Liouville dynamics quickly, because you can't let that jargon slide by.
Ah, right. In classical mechanics, Liouville's theorem describes how a system evolves over time in phase space. Phase space is just a mathematical space where you plot every possible position and momentum a system could have.
So imagine all the possible states of our classical probe as a swarm of bees buzzing in a glass box.
Good analogy. Liouville dynamics says that as time passes, the swarm might stretch or twist into new shapes, but the volume of the swarm remains absolutely constant. The probability fluid is conserved.
You cannot have negative bees.
Exactly. You cannot subtract a chunk of the swarm to shift the center of mass backward. Only quantum wave functions, which have positive and negative phase, allow for that mathematical subtraction. So a classical gravitational field completely fails to reproduce the anomaly. The negative kick relies entirely on wave packet interference of the gravitational field itself.
This raises a massive epistemological question, a question about how we fundamentally know things in science, and it is a debate that is currently tearing theoretical physics apart.
It's a heated topic.
If we run this experiment and we actually observe the negative kick, does a positive result definitively establish that gravity is fundamentally a quantum force? Or does it only prove that specific semi-classical mean field descriptions are wrong?
Because there's a subtle but phenomenally vast difference between proving a theory true and merely proving its alternatives false.
That is the danger of deduction. Some physicists firmly argue that if gravity can mathematically mediate entanglement between two quantum systems, then gravity itself must be a quantum coherent mediator. It must have quantized properties.
But others argue that nature is devious. They argue you could mathematically construct a stochastic classical theory of gravity, a classical field with random, jittery noise built into it, that might somehow miraculously mimic these quantum correlations without the gravitational field actually possessing quantum operators itself.
It's the difference between seeing footprints in the snow and knowing for sure it was a wolf versus just knowing it definitely wasn't a bear. For those of you listening who absolutely love exploring the deep end of these epistemological arguments where physicists scream at each other over the exact mathematical definition of proof, you absolutely have to check out the companion Debate Candy episode on Claire and Neri's show.
They spent a full hour tearing apart the exact nuances of whether observing entanglement inherently equals proof of quantization.
It is a fantastic companion to this episode.
But moving past the philosophical definitions of proof, we need to contextualize why this specific repulsive roadmap is generating such massive excitement in the community, especially compared to older protocols.
Right, because the idea of testing quantum gravity on a laboratory table isn't entirely new. Physicists have proposed tabletop tests before.
They have. The most famous, heavily cited recent example is known as the BMV protocol, named after the physicists Sugata Bose, Chiara Marletto, and Vlatko Vedral.
Okay, let's unpack the BMV protocol. It relies on a concept called gravitationally induced entanglement, or GIE. It is a beautiful, incredibly elegant piece of theoretical architecture, but it is widely considered to be an absolute nightmare in physical practice.
A complete nightmare.
Why? Because it requires taking two massive particles and putting them both into spatial superposition simultaneously. You have to create two separate interferometers side by side.
You have to maintain the delicate coherence of two separate macroscopic quantum states, bring them close enough together that they interact gravitationally without any other forces ruining the experiment, and then measure the resulting entanglement between the two masses.
And the enemy here is decoherence.
The ultimate enemy. Decoherence is the process where a delicate quantum superposition collapses back into a single classical state because it interacted with its environment.
Right, like a stray photon of heat bouncing off the particle.
Or a single molecule of background gas bumping into it. That is enough to destroy the superposition. Managing decoherence for a mass the size of a nanodiamond is already bordering on science fiction. Attempting to manage it for two massive particles simultaneously squares the difficulty.
It is like trying to balance a spinning plate on a stick in the middle of a hurricane, and then deciding you also need to balance a second spinning plate on a stick, while both plates are actively magnetically repelling each other.
That is exactly why this new repulsive roadmap is viewed as such a massive, potentially paradigm-shifting simplification. In this new proposal, we only need to maintain one source mass in a spatial superposition.
The nanodiamond takes the brunt of the quantum burden.
Yes, the probe mass doesn't need to be in a superposition at all. It doesn't need to be split into two paths. It can simply be a highly localized wave packet sitting quietly in one spot.
And the researchers suggest using a trapped Bose-Einstein condensate, or a BEC, for the probe.
Right. A Bose-Einstein condensate is a unique state of matter that occurs when a cloud of certain atoms, like rubidium or cesium, is cooled using lasers and magnetic evaporative cooling to temperatures just a tiny fraction of a degree above absolute zero.
Almost as cold as physics allows.
At these temperatures, the atoms lose their individual identities. They stop behaving like a chaotic crowd of people humming different tunes, and they condense into a single macroscopic quantum entity.
Like a choir singing the exact same note in perfect unison.
Exactly. This provides an incredibly stable, highly localized, extremely cold mass that is incredibly sensitive to momentum changes.
Okay, so only having to coax one single particle into a superposition instead of two feels like a miraculous shortcut. But let's not kid ourselves. Maintaining one source mass in a spatial superposition is mathematically simpler, yes, but physically, it is still extraordinarily difficult.
It's staggeringly difficult.
We are talking about objects that are vastly, inconceivably larger than a single electron or a photon.
To truly appreciate the almost comedic difficulty of this experiment, we have to look at the exact parameter regimes the researchers are proposing in the source text. We have to walk through the raw numbers to understand the physical scale of what is being attempted.
Okay, lay the numbers on us.
Let's start with the source mass. The nanodiamond containing the single nitrogen vacancy center has a proposed mass of around 10 to the negative 14 kilograms.
10 to the negative 14 kilograms. To put that in human perspective, that is roughly the mass of a single human red blood cell. Now, to you and me, a red blood cell is invisibly tiny. But to a quantum physicist used to dealing with protons and electrons, a mass that large is an absolute lumbering behemoth.
It is composed of billions of carbon atoms.
Maintaining a coherent spatial superposition of an object consisting of billions of atoms borders on the miraculous. On the other side, the probe mass, the trapped Bose-Einstein condensate, has a proposed mass of around 10 to the negative 25 kilograms.
That is 11 orders of magnitude smaller. It is the physical difference between the mass of a modern naval battleship and the mass of a single grain of sand.
And they propose keeping these two vastly different objects separated by a distance in the micrometer range, specifically around 0.4 micrometers.
Which is incredibly close.
0.4 micrometers is 400 nanometers. That is less than 1/100th of the width of a standard human hair. It is roughly the wavelength of violet visible light. You are bringing a mass the size of a blood cell and a cloud of ultra-cold atoms so close together they are practically touching, but ensuring they never actually collide.
And the interaction time, the duration, these two completely different physical systems must sit perfectly isolated from the rest of the universe, interacting exclusively through the weakest force in nature, is proposed to be 0.5 seconds.
Half a second. In human terms, half a second is literally a blink of an eye. But in the quantum world, half a second is an eternity. It is an absolute geological epoch.
It really is. Most quantum states, like the qubits we use in early quantum computers, collapse in fractions of a microsecond if a stray photon so much as looks at them funny.
Right, so keeping a macroscopic mass the size of a red blood cell in a coherent quantum superposition for half a whole second while hovering a fraction of a micrometer away from a cloud of atoms. It requires a level of environmental isolation, extreme vacuum, and cryogenic cooling that we are only just beginning to conceptualize.
Let alone engineer. And we cannot forget the brutal statistical reality imposed by the weak value amplification we discussed earlier. Remember that amplification factor?
Oh, right, the denominator trick.
It dropped our successful data retention to 0.0008. When you factor in the incredibly tiny magnitude of the gravitational force at these scales, the actual physical momentum shift we are trying to measure on that, BEC is on the order of thousandths of the probe's initial baseline momentum uncertainty.
It is a tiny whisper in a raging storm.
Exactly. To extract a statistically significant signal from that level of noise, given that you have to throw away 99.9% of your perfectly executed experimental runs, it implies a sheer number of trials that borders on the millions.
You would have to run this impossibly delicate half-second experiment flawlessly,
Yeah.
over and over again, 24 hours a day, for months or even years, just to build up a large enough statistical data set to prove the negative shift is real and not just a random fluctuation.
Because theory and mathematical formulas are beautiful on a chalkboard, but the physical laboratory is a messy, noisy, unforgiving, and cruel place. This is where we have to shift our mindset. We have to treat the experimental obstacles not just as engineering housekeeping or minor technical hurdles, but as the central defining science of the entire endeavor.
Absolutely.
If I am running this experiment and I see a tiny negative momentum shift in my data tomorrow, I am not immediately booking a flight to Stockholm and writing my Nobel Prize acceptance speech for discovering quantum gravity.
Absolutely not. As a skeptical experimentalist, what is your first assumption?
If I see that signal, my first, second, and third assumptions will be that it is a systematic error, a flaw in the trap, or a completely classical, mundane background force perfectly imitating the gravitational signal.
Because we are attempting to measure the weakest force in nature. By definition, that means every other fundamental force in the universe is screaming over it. The electromagnetic noise is deafening. We must run an absolute gauntlet of experimental nightmares.
Let's list those nightmares because they are terrifying. Let's start with the Casimir-Polder force.
Okay, let's unpack that.
A lot of people think that if you create a perfect vacuum, empty space is truly empty. But quantum mechanics tells us that empty space is actually boiling with quantum vacuum fluctuations. Virtual photons are constantly popping into and out of existence.
Right, the vacuum isn't empty.
And these virtual particles exert a physical electromagnetic pressure on surfaces. At distances of half a micrometer, the Casimir-Polder force between the surface of the nanodiamond and the atoms in the BEC can easily overpower the gravitational attraction by several orders of magnitude.
It is like trying to hear a pin drop in a stadium while a heavy metal concert is playing.
Precisely. And if you manage to somehow calculate and subtract the Casimir force, you immediately run into patch charges. In theory, you want your nanodiamond and your cesium atoms to be perfectly electrically neutral.
But in reality,
Microscopic imperfections, tiny structural defects in the carbon crystal lattice of your diamond create stray, highly localized electric fields on the surface. These patch potentials will exert random electrostatic forces that will completely swamp the tiny gravitational signal.
the theoretical proposal suggests shielding the probe, perhaps by inserting an ultra-thin conducting membrane between the nanodiamond and the BEC to block the electric fields.
But introducing a physical membrane right in the middle of a 400 nanometer gap introduces its own catastrophic problems.
Now you have Casimir forces between the diamond and the membrane and the BEC.
The membrane will vibrate, introducing thermal noise. It will heat up, emitting infrared photons that will cause the nanodiamond to instantly decohere.
Exactly. And speaking of vibration, what about seismic noise and phase drift? You're trying to measure a momentum kick so small it barely registers, while keeping a macroscopic interferometer structurally stable to within fractions of an atom for half a second.
A heady truck driving down a highway 5 miles away, or ocean waves crashing on a shore 50 miles away, could create enough microscopic seismic noise in the laboratory floor to violently shake your equipment and completely blur your data.
Thermal fluctuations. Even when the entire apparatus is cooled with liquid helium to a few thousandths of a degree above absolute zero, will cause your trapped particles to jiggle.
The magnetic fields used to create the trap for the BEC won't be perfectly smooth. Trap imperfections will introduce statistical biases that look exactly like the momentum shift you are trying to find. If you see the atoms move, how do you prove, beyond a shadow of a doubt, that the extremely small kick was actually caused by gravity and not just a stray magnetic field?
This is where control experiments become the defining feature, the absolute bedrock of the research. We have to methodically, obsessively try to break our own experiment. For example, to prove its gravity, we would have to vary the mass of the probe particle while keeping its exact electromagnetic properties identical.
Which you could do by using different isotopes of an atom.
Right, like a slightly heavier version of cesium that has a few extra neutrons. Neutrons don't change the electrical charge, but they do change the mass. If the tiny repulsive kick scales strictly and proportionally with the change in mass, that is the unique identifying signature of gravity. No electromagnetic force cares about neutrons.
We would also have to vary the separation distance between the diamond and the BEC to test if the force follows the exact inverse square law predicted by gravity, rather than the steeper drop-offs characteristic of Casimir or dipole forces.
We would have to meticulously map the electromagnetic noise profile of the exact laboratory setup by running the entire experiment without putting the nanodiamond into a spatial superposition, just to establish a baseline of how the atoms jitter naturally.
The burden of proof to definitively distinguish random electromagnetic noise from genuine, verified quantum gravitational entanglement is astronomical.
It really is the ultimate needle in a haystack. Except the needle is made of the weakest force in the universe, and the haystack is made of screaming, chaotic electromagnetic interference.
Yeah.
But if we can isolate it, if we can shield the electrical noise, control the seismic vibrations, perfectly manage the decoherence for half a second, and successfully execute that brutal 99.9% post-selection data purge, the payoff is nothing less than a fundamental rewrite of our understanding of reality.
Before we conclude, we must firmly, unequivocally reiterate the boundaries of this physics one last time. The unconditional experiment, meaning if we run this setup, but we do not perform the post-selection filtering at the end, if we just look at all the data, does not create a free repulsive force.
Right. Momentum conservation remains perfectly mathematically intact across the entire unfiltered ensemble of particles.
The anomaly strictly and uniquely appears in the mathematically post-selected subset. We are not uncovering a method for propulsion, we are not violating Newton's laws on a macro scale, and we are not building a levitation drive. We are exploiting quantum statistics to reveal the underlying nature of the gravitational field.
So, to truly claim victory, researchers are going to have to pass 3 distinct massive milestones on this roadmap. Milestone 1. Observing the anomalous negative kick in a physical laboratory, successfully overcoming the sheer wall of noise and decoherence.
Milestone 2. Showing definitively, through the rigorous isotope and distance control experiments we discussed, that the mediator of this kick is strictly gravitational and not a Casimir or electrostatic artifact.
And milestone 3. Demonstrating, theoretically and mathematically, that absolutely no viable classical or semi-classical mean field mediator could possibly reproduce the exact statistical correlations observed in the data.
Passing those 3 milestones would mark the end of a century-long, agonizing search for empirical evidence linking the mathematics of quantum mechanics with Einstein's general relativity. It would be the crowning achievement of modern experimental physics.
I want to leave you with a lingering thought to mull over as you go about your day. For decades, we have assumed that to find quantum gravity, we had to look in the most extreme, violent, unimaginably energetic places in the universe. We thought we needed to look deep inside the crushing event horizon of a black hole, or rewind time all the way back to the infinite singularity of the Big Bang, where infinite density forces gravity into the quantum realm.
It seemed like the only way.
But maybe we don't need a black hole. Perhaps the very first empirical, undeniable glimpse of quantum gravity won't be a cosmic cataclysm. It might arrive simply as a tiny microscopic particle, hovering quietly in a freezing, isolated laboratory, quietly moving the wrong way.
For more science candy, companion debates, news briefings, and classic audiobooks, visit clarinaratio.com.